Yes, it's perfect. Do you have videos or?
It should work though. It's
Okay.
yeah. Well, okay. I'll quickly try so that we can see. That works now.
Yes.
Yeah. Okay.
I see Philippe is on. Maybe he has some technical issues. We can't see.
Okay. Yeah.
Sorry, Philippe. Philippe, he said he has some technical issues and he can't turn on his voice. So, but the time is already started, so I will make a brief introduction.
Yeah, sounds good.
And he will join later, maybe for the later discussions.
Yeah, sounds good.
Okay, so everyone, hello, good afternoon to our students and our guests. So welcome to the master class at Tongji University. The name is Advanced Debate on the History, Theory, and Methodology of the Digital in Architecture. So the course is led by Professor Philippe and me. It focuses on, in this semester, we mainly focus on performance-based design, and the course is divided into 4 parts: environmental performance, behavioral performance, and today's the structural performance, and later we will also have the material performance. So today is a great honor. We have the really kind of great opportunity to have Professor Philippe from ETH Zurich to give us one of his 3 lectures in the coming weeks. So today his topic is about disrupting concrete construction, digital, sustainable, and circular. So before we start, I will just briefly introduce Philippe Bloch, although he's the person do not need any kind of further introduction. So Dr. Philippe Bloch is a professor at ETH Zurich, and where he leads the Bloch Research Group, BRG, and also he is the head of the institute. Philippe is also the director of the Swiss National Center of Competence in Research, Digital Fabrication. He studied architecture and structure and engineering at the University of Brussels and also at MIT US, where he earned his PhD in 2019. So with no further ado, please join me and welcome Professor Philippe. Philippe, the screen is yours.
All right, thanks a lot for the introduction and thanks also for the invitation. I'm looking forward to sharing some of our work, but maybe first also I will be with you for the next 3 weeks. And so what I thought was today, I will focus on how we approach design and specifically hearing the focus of this class. I will cover every single aspect. So I will cover how computation is important. I will cover how we find it important to design, including all the constraints of, for example, structure and fabrication from the beginning in your design framework. And then last but absolutely not least, the core emphasis of my lecture will be on how to really achieve sustainability targets and not incremental, but really to try to disrupt. I thought today that I prepared a shorter lecture than what I typically would do for an hour and a half, because I hope that there can be good discussion. So I really hope that we can have a Q&A afterwards, and that you can really ask all the things that are not clear, or where you're maybe a little bit skeptical even, or where you want me to give more follow-up information or discussion. And then the next 2 weeks, so next week I will be focusing on graphic statics techniques, because that is one of the ways that we embed structural information explicitly into our designs. And then the third week, I asked co-director of the BRG, so Tom van Mele, to come in and to actually talk about our approach to computation. So he will give a very small introduction to Compass, but more importantly, explain our attitude towards computation and how we believe that we need such a new open-minded, open source kind of attitude to computation, to sharing, to collaboration, and so on. So I just wanted to start with this by sketching out a little bit the 3 weeks that we will be talking about. Okay, but let's dive in today. So as I said, today will be about sharing our integrated approach, and with a very clear target of sustainability. And I will do this through our projects in concrete specifically. I probably don't have to tell you this. This surely was an important starting point for this class, that our industry, these are global numbers, are responsible for quite a lot of negative impact and pressure on the climate. We're responsible for, these are approximated numbers, but it's easy to remember, 40% of the global human-made greenhouse gas emissions, the resource consumption. So that means the single-use resource, right? Global waste production, particularly construction demolition waste is adding there, and then also energy. But what I will be talking about today is what I believe is the key bottleneck, the remaining bottleneck, is the embodied emissions. Why I say that for me this is really the key bottleneck is because there is actually a rather straightforward solution. There has been for the operational energy. So there has been so much research, so much development on efficient heating, cooling systems, on better insulation, but also if we were to go to renewable sources of energy. And I just recently, maybe that is old news for you, but I read in the news that the largest solar energy plant was just opened in China. So that is exactly what I'm talking about, that if if we can reduce the impact of that energy, then actually, theoretically, we would have a solution to solve the entire operational energy emissions. But all of this gray energy, as it's called, is embodied emissions. We don't have a very clear solution there. I would like to start as a framework that I will be coming back to throughout this presentation. This slide that I borrowed from my colleague Catherine de Wolf, which talks about, which for me really nicely clarifies the three main levers that we can use to reduce the environmental impact of a building, of a construction. So the first one is the one that most people focus on, is to change the materials that we use to go to low carbon materials. And I will talk about this later as well. Second one can have a much larger impact, that is actually to reduce the amount of materials altogether that we need. And that's where structural optimization, structural design, appropriate design comes in. And then the last lever, this one, I believe, is probably one of the most important ones indeed, is to actually expand the lifetime of your resources, your components, your structures. So the last one has to do with, of course, circularity and circular thinking. But why I wanted to start with this slide here is because it really shows that you can get some improvements if you, for example, just look at structures. You can have some improvements if you try to tweak the materials, but the real big impact will come if you find ways to design with a combination of these three different levers at the same time. Then your impact will really accumulate. So I mean, the circular concepts surely are known to you, but I just wanted to put this in as a reference. I like this very clear, as it's called, a butterfly diagram here, presented by the Ellen MacArthur Foundation, where I also think it's important to show that there is not just one definition, not one interpretation of or one approach to circularity. There's many cycles that we can activate, and some of them are more efficient than others. So you see that, of course, the one that is very known is the biggest one, is recycling. But of course, keeping buildings updated so that the refurbishing, reusing of components, maintenance, so that we don't have to do anything, is a smaller cycle. So kind of what you want to achieve is the smaller cycle, but any of these cycles, of course, allow you to keep resources into the loop. And I think that is very important. But what I am convinced, and of course I'm preaching to the choir, because Philippe is a global leader in also demonstrating the importance of both rethinking how we design and also how we build our structures. So both aspects are important, and that is because both aspects are, of course, important to control the three levers that I talked about earlier. But so today I will show you how, and this is an example, right? So see everything that I show you today, try to see beyond the specific results, but try to also understand the attitude or the approach behind it. So these are three key topics, how we as a BRG approach these challenges. So the first one we call strength through geometry. The second one is material effectiveness. Already do notice that I use the word effectiveness and not efficiency, because efficiency often is referred to as lighter, but building lighter is not, or less materials is not necessarily always solving your problem. If you use very high impact, carbon footprint materials, but very little of them, it might actually cancel out the effect. And then the last one, I will show you how I really believe that we have to also fully embrace circular construction and how we do this in our work. So the first one, strength through geometry. Sorry for those of you that I have seen already some of my presentations, but I want to set the stage and kind of show that I believe very much in learning from the past and in in also assessing traditional techniques, things that make sense, things that were realized in a time where there were constraints, when not anything was possible as in the last decade. And this is such a beautiful technology that somehow was forgotten, how to build these vaulted geometries from the past, why Gothic cathedrals are still standing after 500 years and so on. So these beautiful structures stand because they have a good geometry, not because you use high strength materials or you reinforce them in very clever ways. No, because they have this structural geometry that make them stable and resilient after centuries. But so considering that these shells are literally proportionally as thin as an eggshell, this was for me an important trigger and motivation to bring this knowledge back to modern design and engineering. So in order to do that, we have spent the first 10 years. So now I've been almost 14 years at ETH Zurich as professor. And the first 10 years we spent with building a lot of prototypes and pavilions to really push ourselves, but also push the acceptance and the understanding outside. So the first project that I wanted to show in the context of strength through geometry is the Armadillo Vault. What you're looking at is a stone vault, unreinforced, out of 399 cut pieces of stone that is assembled without mortar, without glue, without reinforcement. So why I start here is just because this is an extremely pure structure following the same logics as why the cathedrals are still standing. And we did this to indeed make that point, to show, like, haven't we forgotten something, and haven't we shouldn't we reintroduce structural geometry to activate humble materials in a safe way, again, as was done in the past. So, but the background for this is a long development of tools that allow us to rediscover that structural geometry. So tools based on graphic statics. Again, this will be the topic of the second week of next week. I will be talking how these tools allow you to, in an open way, really understand how the forces flow by manipulating them and so on. And these tools were then translated in a tool called Rhino Vault by my late colleague, Matthias Rippmann. And what we there want to do, and this will be a focus next week, I will show you how I think it is very important to not build black boxes of tools where you don't fully understand all the parameters, but we try to actually clarify how these things are being developed. Maybe also worth mentioning in the context here is that you almost never, and I will come back to this later, there is never just one target, not even in a simple pavilion, surely not in a big building, is that you cannot just focus on structures. You also have to think how to fabricate it, how to optimize fabrication to make it in a timely manner, in a cost-effective manner, and so on. And here's some images how we really kind of looked at the most efficient ways of cutting this stone in order to realize this project in just a couple of months. But as you see here, the stones were assembled without any mortar, glue, any mechanical or chemical attachment so that it could be taken apart. So here's some images of how this then looked. This specific geometry that had to do with fabrication. But the key message why I wanted to start with this project is because the first message here is that by getting the geometry right, we can actually significantly reduce the mass needed to realize a structure. Maybe a quick side note here, because this just happened 2 weeks ago, because it was dry assembled, and I will come back to the importance of that later. This entire vault was taken apart, and just 2 weeks ago, I heard from my colleagues in Texas that this vault has been sold to a client in Dallas, Texas, and it will be installed in a park in the next half year. So super exciting that this Armadillo Vault will have a new home, a new permanent life in someone's beautiful garden. A second project in the context of, so remember, I'm now trying to argue why we should care about strength through geometry. A second project is an experience I got to work on this beautiful project Mapungubwe by Peter Rich Architects, John Oxendorf and Michael Ramage. I was asked to do the safety assessment of these vaulted structures. What you're looking at here are soil press tiles that are built using a Catalan vaulting technique. So this vaulting technique is globally known. Here, for example, but it comes from the Mediterranean. So it's a traditional technique where what you're looking at here is actually not just decoration, but one of 3 layers of tiles that are placed without any formwork. So here, this is the oyster bark in New York City. And the technique uses a fast setting mortar to have these stable kind of boundary conditions to them built in stable sections. And so that is the technique that was introduced there, because it was a very remote site, and we were asked to use only local resources, so local material and local kind of labor. So this is how this works. So the timber that you see is just guide work to guide the masons to build this geometry like that. And so here first results. But why I want to, in the context again of setting the stage here and strength through geometry, what is unique about this project is that the tiles were designed to really reduce the amount of imported engineered materials. So here you see the local neighborhood, so the people in the village nearby, to press these tiles with a manual press using only 7% of cement to stabilize that local soil. And so this was very important to reduce, and also, of course, the energy input. There is no firing, so these are unfired tiles. And the reason that I explain a little bit how they work is because these tiles are extremely weak. They are only designed to take 2 megapascals in compression, which is 10 to 15 times less than our typical concrete. But if you see here on the left, if you place your material, if you place the material where the forces naturally want to flow in compression, then you don't have stress concentrations. You actually activate this material very nicely. And so that is also why on the right, the women of the town are carrying these tiles in very small packages because the tiles would just break in bending in front of you. So they have almost no bending capacity indeed. So next week, I will talk on how one can design and what is important in getting the geometry right, as I am presenting it here. So compression only geometry. So how we find the arch geometry, but also how we can assess under what loading cases it is stable. Like, for example, here under a live load, the arch would not be sufficient to contain this. What this red line is called a thrust line. It's the resultant of where the forces in compression would want to flow to the supports. And if we can not find a solution within the geometry, then that means that we would have an issue. This would lead to collapse. And there's different ways to kind of then add a stiffening scheme, as this is called, to the arch. So how we can basically provide load paths for loading cases other than the design load. And so again, that is also important to consider, that form finding is amazing, discovering a good starting geometry, but it is obviously equally important to have a very rational kind of way to bring
严超，听得见吗？严超，听得见吗？
可以的，应该是他那边网卡住了吧？他现在好像掉线了。
下次要交给他装那个腾讯才行。可以马上接一个邮件过去吧，问一下。
好的，我们发个邮件问一下。
Okay, apologies. I really don't know what happened. Let's try this again. Hi, Philippe.
Hi.
Hi. Let me continue. Sorry about that. Okay, sorry everyone, but let's continue with where we left off. So I was talking about the importance of a stiffening scheme to provide alternative load paths to your through the structure. And then by just adding a tension tie, then what we just did is we replaced our typical reinforced concrete floor plate or beam by a structure that uses 70% less concrete, right? So this is a very simple principle, a historic principle, but that allows us to already get these achievements. So this was a core starting point here of the structure. But the key message that I wanted to make here, so the first example was to show that if we get the structural geometry right, that we can activate, that we can significantly reduce the mass of the structure. And then here the second one is that you see that again, we reduce the mass, but on top of that, we have extremely low stresses, which allowed us to use this local material, this low strength material. And there is almost a one-to-one relationship between how much embodied emissions or carbon footprint the material has and how strong that material is. So by activating weaker materials, low strength concrete, for example, we can significantly reduce what is called the embodied carbon coefficient of the material. So that is a second reason why I really care about reintroducing structural geometry. So we recently, this was a project in 2021, again, in the context of the Venice Biennale, we did Striatus. And I wanted to, and there's of course, again, some amazing work being done by Philippe and his team here with you in Shanghai. But what we wanted to show with this project here is I consider concrete, so not reinforced concrete, but concrete, the compression part, as an artificial stone, which is indeed happy like in compression, like a brick, like a stone. So what we wanted to show with this project that we did together with Zahadid Architects was that instead of considering 3D printed concrete as a formwork for the real structure, we wanted to show that if you understand concrete as that stone, then you want to design it as an unreinforced masonry bridge. So this is a fully unreinforced concrete 3D printed structure. So in order to achieve this, we apply concrete logics at two levels. So on the level of the global discretization, we actually have a masonry system like a Roman arch, but then also on the level of the printed layers, we basically have a perfect alignment through this 3D printed kind of structure. So that means that we used all our masonry kind of knowledge and toolbox, and that is maybe why I showed you this before, to design this kind of geometry. Just a second, I see that I have an issue. Let me quickly try to clarify. Okay, yeah, no, so I made a mistake with my lecture, but it's okay. We'll just continue like this. Wanted to show you a few more other things, but maybe I can catch this up next time. So apologies about that. All right, so but in order to achieve this, we use this concrete 3D printing, non-standard, so non-parallel concrete 3D printing, and of course,
sorry, Philippe. What we are looking at is the presenter mode. So we see two slides.
Okay, do you see it now?
Yes, that's perfect. Thank you.
Okay, sorry. Thank you for that. So, or maybe I'll share the right screen then. Perhaps that's maybe better. I'm really messing this up today. Apologies, everyone. But we'll get there. So here, this one, desktop share. So now you should see the right screen, right?
Yes.
Okay. So what I wanted to say here is, again, what's important to consider is that we have this masonry on two levels. And so we encode these constraints really in the print paths. So what we do is globally, we control the discretization like a masonry stereotomy, and that defines your start and end planes. But then anything in between, that is what's shown on this slide. There we actually let the constraints of the printing logic kind of speak. So that means that anything in between the geometry is implicit. So we don't control the geometry that we slice, but we actually generate the geometry based on the print paths, how much overlap can every print path have, what is the perfect length of the print path to make sure that the speed is correct and the hardening is correct, and so on and so on. So I just, and sorry, that's the slide that I was looking for, but I want to say that here you see this maybe is that globally we have this discretization that gives you these start and end planes, and that is important to have globally a compression only structure, but then locally you really want to make sure that everything is printable. And so we embedded all of these constraints into our design framework so that every single block would come out, as you can see, very cleanly, very precisely, and without any issues. But so then of course we have a situation that we can really celebrate all the opportunities of concrete 3D printing. Here on the left you see that. And remember, the stiffening scheme, we add, for example, stiffeners to increase the structural depth, but we don't want to add all of that mass. We just need it to provide load paths to the structure. So here on the left, you see that we hollow out these structural elements to really effectively increase structural depth without adding weight. So that is possible with this 3D printing. So you see that we can place material only where needed left. And then on the right, again, you see these print paths are not just straight, also they're both inclined in two directions so that they really are aligned to be as orthogonal as possible to the force flow. But so that another thing which is very powerful about concrete 3D printing or 3D printing in general is that this 21 meter in diagonal kind of bridge with 53 blocks was printed in a total time of 84 hours, right? So this is another aspect that is important to kind of emphasize, is that in this rethinking how we build, also being much more efficient on how we go to the building site, what is done in prefabrication, what is done on site, how fast can we deliver is a crucial aspect that we need to change. So, but that means that then we had these super lightweight 3D printed elements that could be assembled very simply, and we assembled them without any connection again. So we only have, you see here on the left, you see this little black kind of interface material. You see this here as well. This interface material is to distribute the stresses so that there is no local stress concentration that can cause a crack. And the reason that we dry assembled it is because I wanted with this project not just to make a statement about concrete 3D printing, but really about highlighting that if we use concrete as the artificial stone that it is, so we really appropriately use the material, that we can really offer all kinds of circularity opportunities. So the first one is is the one that most people focus on. Can we reduce? Can we reduce the amount of material? Can we reduce the amount of molds to realize this structural geometry and so on? But if you indeed, like what we demonstrated here, if you keep materials separated, so if you don't have embedded reinforcements that can corrode after time, then you can have a very clean maintenance and repair strategy. If you dry assemble and use the masonry logic to have a beautiful, not only self-registration, but also a stable connection without needing any glue, any mechanical fasteners, then you can take it apart again. And that means that you can reuse all the components. Maybe you might think, what is the purpose of reusing this bridge? But more globally, you will see in the second main project that I show you later that reuse of prefabricated elements is a very important outlook for the end of the lifetime. And then lastly, something that we have done in this bridge is we have basically designed this bridge to easily be taken apart and easily recycled again because of this clean separation of materials. So this is then how it looked like. All these features had to do also with some fabrication optimization, but I want to keep kind of going forward, so I will not talk about those today. But look again here at this image, right? So why we managed to build this pure structure is because we were consistent throughout, and we had a fully integrated pipeline that made sure that we globally have this masonry discretization orthogonal perpendicular to the main arches, but then also on the level of the elements we have this perfect alignment. And as I highlighted, treating concrete as a masonry system, a discrete masonry system, gives you all kinds of circularity opportunities. So again, appropriate, I think, for the context of this class is that all these things don't just naturally come together. We don't design something independently from the engineering logic. We don't design something that we need to still check if it can be fabricated or figure out how it will be fabricated. And so here, this project was a very holistic kind of approach with 3 different teams in 3 different locations. This project was done in the height of COVID. So the different teams actually never met. They never met in person. We did the entire project over Slack, over computationally. And what I want to point out here also is that we actually condensed the process by, from the beginning, talking about the interfaces. What does the engineer need? What does the architect need to discover all the possible iterations of design? What are the constraints of fabrication? And all these kind of interfaces were kind of discussed from the beginning so that the 3 teams could develop at the same time. And then at the end, everything could be brought together. So the 3 main teams were our group, the BRG, then Zaha Code, the group of Shajeh Bushan, and then Incremental 3D, the concrete fabricators from Innsbruck, and then the sponsoring, but also the specific ink was done by Holcim. So, but how we managed to actually bring all of this together in a very coherent and very robust way, because this project was just so fast. I mean, I know you guys do things very fast as well, but there was really not a lot of time here for this project. So this came together with Compass. And again, I asked Tom to come in the 3rd week to actually share how we set these collaborations up, why we set it up in such a way, and how I hope you can learn perhaps also from these approaches to computation. And we specifically use Compass, this open source computational framework, but more about this in the third week. I wanted to share something that no one has seen because we are building a permanent bridge with a 50-year design life in Lyon that is Striatus 2. It's called Phoenix. And Phoenix because it will return from the ashes. The new bridge will be 100% construction demolition waste, so it will be printed with no new cement, no new aggregates. So everything will come from the old bridge and other construction demolition waste. And what I'm showing you here is for us a key bottleneck of actually really celebrating and showing the opportunity of concrete 3D printing is also optimizing the assembly on site. You saw that we had this rather inefficient scaffolding, this waffle structure to assemble the bridge. And so what you're seeing here is we're developing a very robust system that uses more than 90% rented standard scaffolding elements. And then we just have these little baskets that we make, very lightweight baskets, where we already assemble multiple pieces at the same time, so that in a very controlled environment, so not in the air, we can already pre-assemble the structure in big chunks, and then it's being lifted in very controlled few maneuvers. So this will really not only speed up the assembly, also improve the tolerances and the control, but most importantly, get away from almost all single-use materials. So just this small strip, these small baskets that we made to assemble the structure. So I wanted to show this a little bit because I also am we are continuously evaluated, self-critical. We're kind of evolving to really push the state of the art, but always step by step. Okay, then the last key project is Hilo. That we just realized. Maybe I'll talk first a little bit about this roof. What's special about the roof is that it's a shell structure, a very thin structure, a double layer shell. So we made actually a sandwich shell that is connected only with these steel kind of connectors. And you will see that these steel connectors also have something to do with how this roof was realized. And then the two layers that you see are 5 centimeters and 3 centimeters only of concrete to cover almost 180 square meters of roof. The thing that we wanted to show with this roof was that getting the geometry right, surface structures in concrete are very efficient, but also need a lot of scaffolding, need a lot of support to build it. And unfortunately, this mold that lasts only 28 days often turns into this after the concrete is hardened. So what we wanted to show with this project is, can we get away from this single-use material and the inefficiencies also on the formworks needed, on the foundations needed, on all this scaffolding and so on? Can we resolve this with a flexible formwork? So we developed this kit of parts, this tension system that allows, just with very light, simple, reusable parts, to realize this shell. And on top of the shell, we put then this fabric. This was still in the hall when we did the one-to-one prototype. I'm happy to talk about this as well, that I believe that innovation doesn't just happen in one day. It's always a lot of development. It's building up of knowledge, but also of trust and experience by building real scale prototypes. So we have done a lot of this. So here you see this full scale prototype in our hall at university at ETH. But then the same kit of parts tweaked because we updated the geometry. We learned from the prototype. So 85% of the pieces could be reused to then make the formwork of the final structure. Again, putting the fabric in, and finally we could apply the concrete. In this case, just to be clear, this is not a compression only geometry. It's more kind of like a Felix Candela shell. And so here you see also that the first layer, because we only have one layer of super thin reinforcement, the first layer has quite some fiber in it to make sure that we don't have any small cracks and so on. This was just after decentering. But I wanted to talk a little bit about this roof, so I didn't give you too much detail, but I wanted to talk about this roof because for me, the key thing that we achieved there is that this is an innovation that didn't happen in a clean kind of prefabrication workshop, but it happened on site with real contractors. And the key that this worked is that, and here you see an exploded detail of this node in our kit of parts, is that we developed a node that had these elements, these vertical elements that allow to work on site to reduce the complexity of your crazy roof into something simple, because you always had this reference, this local reference on what to do, where to attach the reinforcements, how thick does my layer need to be, and so on and so on. But Tom will talk about a little bit about this project more, because this project was done very consistently using compass for everything. For here you see on the top left for the form finding of the cable net formwork, for the constrained digital fabrication and making sure that these thousands of components all come out perfectly and have all the constraints that you need, to couple every single iteration with a finite element analysis to make sure that it works and we can really explore the design freedom, but also to kind of include new ideas of the control system that was used to pre-tension the fabric. But Tom will focus much more how Compass was used to coordinate more than 40 subcontractors, many of which had absolutely no digital expertise or complex geometry expertise. So this, again, Tom will talk about this in the third lecture. But so this is the roof, but why we are so excited about this project is because of the floors that we showed there. And maybe quickly zooming out here, we all know that our population is still significantly growing and that we're expected to be at least 2 billion more people by 2050. Bill and Melinda Gates calculated in 2019, and this is of course a calculation based on how we build right now, but in order to provide all the housing and infrastructure for all these people, we have to build the equivalent of 1 New York City every month for the next 40 years. So that is a gigantic challenge. This is an image of your home, of China. You see also that means that we will have much more dense areas, cities all over the world, as you're witnessing yourself. And that is actually what I quickly want to talk about. So let's look at this building, the typical medium high rises, so 20 to 40 stories that are popping up all over the world. If you look at these structures, you see something really remarkable, that at least 3/4 of the mass of that building is in the structure. So that means that the structure is there to keep itself up more than anything else, more than the finishes, more than the users, and so on. And if you zoom into that structural mass, then you see that more than half of that structural mass is in the floors. So 40% at least globally of the weight of all these buildings is in the floor plates, right? So again, considering that more than 2 billion square meters of these floor plates will be built in the next 30 years, can we do something about this? Can we build them more efficiently than what we have been doing now? So this is maybe a moment to talk about material effectiveness and talking about concrete. I don't know how it is in China, but in where I come from, where I work here, there is a very active concrete shaming going on. People say that concrete is bad, bad, bad. You shouldn't build in concrete. Well, it has a really large impact, but is it correct to just talk about the material? So is concrete the most destructive material on earth? Is that correct? So you probably already can imagine where I'm going with this. If you look on the left, and both are per unit mass. So these are on the energy side, the embodied energy, and on the right, the embodied emissions, then you see that concrete, and this is even traditional concrete, this is not the new types of concrete, is quite good as a material. In fact, it's one of the best materials. So maybe it's not the concrete itself that is the issue, but it's how we are using concrete. And so I argued before that I consider concrete as an artificial stone. A stone is happy in compression. So these kind of geometries, but also constructional logics, will really make a lot of sense for this material. And indeed, by not forcing this material to be in a geometry that it doesn't want to be, you need to add all of this this additional volume. So we already looked at this in the South Africa context. But what I didn't emphasize is that it's not just about not having this natural flow in compression, but also you're forcing a certain force flow that also needs 90% too much steel. And that is not unimportant because the steel is significantly higher, both on the energy and certainly on the emission side. And the one, by the way, that I'm highlighting here is 100% recycled steel. If you go to virgin steel, then this would be not 10 times higher than concrete, but 30 times higher than concrete. So this is important to look at here. So, and when you start to reduce and optimize, then you will see that actually the component, the contribution of steel is really significant compared to indeed once you start to use the concrete how it wants to be used in compression. So we developed this in 3D. Again, I want to emphasize that the compression part is entirely unreinforced. So same principles as in the bridge, we separate the compression flow from the tension flow in order to have clean materials that are easily recyclable, that are aligned to where the forces want to go, that are nicely kind of low stress also, so low strength material. By the way, just to clarify here, right, that the global geometry is a vault, which is the 3D version of the arch. And then the stiffeners, they, as you can see here, they nicely accumulate towards the corner, right? So that is how this geometry was generated. And so we 3D printed this, we did all the tests. And here you see 1,200 kilograms of ETH inert standing on 2 centimeters of unreinforced, super low strength materials. And that is basically what we have done for these floors, right? So these floors, if you're in Zurich, go visit this building and go check out these floors, because now you know that this 5 by 5 meter span is spanning with only 3 centimeters of unreinforced low strength concrete. So this is what you see here. I included a few kind of slides that are kind of confidential, but I thought it was maybe important to show you a little bit more insights than the typical overarching lecture that I give. So here you see some details how it works. You also see that we embedded some hydronics, some heating and cooling that allows us really to activate this surface to really kind of get more out of the concrete. But I want to say that this is something that I would never do again. And I'll explain why. I think it's important that you don't embed things that make it harder to recycle, but also make it harder to upgrade. So here these pipes are embedded in the concrete. That means that if we want to try another layout, or we need to upgrade the system, or we want to change the system, then these pipes are stuck and you cannot do that. Another thing that is of course important is that, and I mentioned this earlier, is that we don't just want to look at structural conditions, but also non-structural ones, for example, acoustics. And typically lightweight construction has an issue with contact noises, with low frequency noise transmission. And here what we're doing, we're actually using structural stiffness rather than adding mass to be very efficient in acoustics. So this is showing for the 3 centimeter naked shell that we already have an effective reduction of 42 decibel. And then of course, with all the typical finishing layers, we're perfectly fine. So that also means that compared to other lightweight structures that don't have this structural stiffness to be very efficient for acoustical reasons, that we will always be lighter. Because in the Eurocode, they require 350 kilograms of square meters on average to guarantee acoustical kind of performance. But here we don't have to reintroduce that material. So what I'm saying about reintroducing, a lightweight timber structure, when built here, you have to add material to it in order to solve the acoustics. That is why actually in timber construction, you often have these hybrid systems with this additional concrete on top in order to solve acoustical, but also thermal kind of issues. So again, zooming out a little bit, why I'm so excited about what we showed there is because if you again look at these buildings, and let's take a 25-story building, then you see that we will be using that 40% of the mass is in the floor. I talked about this, but we will also take these reductions. Here you see that we don't have 70% and 90%. That is because here we are designing for a 2-hour fire rating. So we need to reintroduce a little bit more material. But if we were to replace the typical reinforced concrete floor plates with the system that I just have been showing to you, this compression-only floor plates, then you would save 7,500 cubic meters of concrete for this building, which translate to more than 1,200 concrete trucks that would not have to go to this one building, site. Or per floor, you can save more than 20 kilometers of reinforcement, and that means rolling it out from Zurich to Brussels, which is more than 600 kilometers of reinforcements that you would save for this one building. But again, let's not get ahead of ourselves, because I made a big statement in the beginning that actually it's not just the mass, the volume that matters, but it's both the volume and what you do with them, and what type of material you use. So it's both the mass, M, and it's the embodied carbon coefficients, the ECCs. So summarizing what I've been trying to argue is that through structural geometry, you can of course work directly on the mass. And then the embodied carbon coefficients, you can of course start to change the materials. And there is so much rapid developments in concrete development, all kinds of clinker replacements for the cement, alternative binders, calcined clays, the use of industrial waste products, and that actually you can really get much better concretes today than the ones that we used to use 5 to 10 years ago. But another thing that I've been talking about is that if you get the geometry right, you also can reduce the stresses. And that also allows you to activate lower strength, lower carbon footprint kind of materials. So let's look at what that means for this floor plate. So the first two aspects come from strength through geometry. So less mass, that's directly this volume reduction in concrete. Lower stresses, so going from a more typical C30, 37 to a C16, so really a low strength concrete, gives you an additional reduction of around 20% on the global warming potential. And then with the new types of concrete, so not the typical CEM1, the ordinary Portland cement, but for example, the CEM3 or 3+ kind of mixes, you can reduce the impact of the material itself by roughly 2/3. So that means that on the concrete, we have a global warming potential component of only 9%. And then, of course, we have the reduction of the steel. So that means that we now, by reintroducing good structural geometry, we have a floor plate that can reduce the global warming potential of our typical floor plate by 85%, 85%, right? So this is not incremental. And I want to maybe show you how typically things are done. So on the left, that is for me, I call it the easy win. It's the low-hanging fruit. If you only focus on the material, then you have the same mass, and you have a significant, but you have an impact on the global warming. On the right, you see that actually we have a bigger, of course, performance improvement on where it really matters, but also on the mass. And this mass improvement is very important. I'll show this in a real project, why this mass reduction is also so important in actually achieving a way to introduce your innovations into practice, into real projects. So last point, circular construction. So I'm happy that we are, and literally I'm not making this up, we are a couple of weeks away of setting up a company to commercialize these new floor plates, which we call the Rippmann floor system, the same Matthias Rippmann, our late colleague that designed Rhino Holt. So what is special about these floor plates is that we take all of the things that I've been talking about today together to make the most efficient system here. So it's prefabricated so that we can have a fast installation. It uses low strength, so low carbon material. We do a full separation. So we have no glues, no kind of connection between steel and the elements, so that we have this clear circularity that I argued. It's fully unreinforced, which is important towards durability. So we have no issues with potential corrosion, fire safety of the steel. And it's dry assemble. Again, remember this reversibility and so on. So this system is now already being implemented in, this is a real project. So in Brussels, we're designing a 130-meter tower that has been designed entirely around this floor plate. But why I show you this slide here on the right is that the client was because this is a totally new concept, the client asked us to develop 4 towers in parallel in order to have all the comparisons. And it's extremely clear that we come out not only on the sustainability targets, but also on the cost. We are so much better on the cost than any system, including timber solutions and so on. So the biggest competitor actually was the hollow core, so the highly optimized pre-stressed simple floor plans. But compared to them, we can still be 20% lighter, and we have significantly lower embodied emissions. And then again, that translates also a big impact on the lower emissions of the entire building. Also, by not just layering all the systems, we actually can reduce the floor-to-floor height, something that is super important for clients, that you don't have a taller building, that you can squeeze in more floors in the same height. So this is, of course, to also rethink how you integrate building systems. And the reason that we can do that is that we can activate all these cavities where typically structure is, to now start to have these building systems elegantly integrated. So here you see a part of the section. This is only part of the tower and the floor plan. A second project that is even further in development. So by the way, look out for this. We are only going to the building site in 2025, but we are now building a full-scale mock-up of 2 of those bays, so a 200 square meter mock-up together with the contractor. So we're doing a tendering phase. More importantly, perhaps, is this competition that we have won with Gigant here in Zug. And this 10-story office building, as you can see, was also designed around this floor plate. So, but what is exciting here is that we really had to do a lot of work in benchmarking it compared to all different floor plates. And you see that we are doing significantly better. Even considering the dark gray is actually the standard transport amount that we need to add in Switzerland to follow the regulations here. But what we will be trying to do is to set up a local prefabrication factory so that we can get these emissions down as well. You also see the timber solutions are not that great, because for 8+ meter spans, you need so much glue, so much steel and so on, that you have single-use materials that will not be able to be reused or recycled in an appropriate kind of way. So that means that their impact is actually still rather significant. Of course, much less than a reinforced concrete floor plate, but just to make this point here as well. And I'm happy to talk about this in more detail later as well. But what is super exciting, and I'm excited to show this to you, is that in this project, the entire team actually did a very careful analysis of what would be the real cost of the entire building based on all these different systems. So here on the left, we have the reference, super standard, super optimized kind of reinforced concrete floor plate in Switzerland that costs 174 Swiss francs per square meter, right? And then what Mike Guyer did, he said this RFS, this new floor plate, costs 280 Swiss francs per square meter, so significantly more expensive. So the client already said, whoa, this is not going to happen. This is this is way too expensive, and so on. While we actually calculated that the real cost of the floor system is only 160 Swiss francs per square meter. And this has been approved, this has been tested by external consultants. So you see that we can do better than your typical reinforced concrete floor plate. And that is because we use so little material, because we can build it so efficiently. We don't need scaffolding, we don't need formwork, and so on and so on. So that is the real cost. So I did not understand why my Guyer said to the client, the cost of the floor plate is 280 Swiss francs per square meter. But basically what he was doing was that he showed that with this significant increase, so you see that he increased the real cost by almost double, right? But even with this very high cost on the floor plate, the total cost of the building remained the same. And that is because these floors are so light, because we can optimize the assembly, we can reduce the columns, we can reduce the foundations. So even though that element per element, the cost is almost double, the total cost of the building is the same. And I think this for me was a very important also lesson, is that we need to try to both for the sustainability targets and for the cost targets, we need to argue on the full scope, the full life cycle, or the full cost of the building to really introduce an innovation. Of course, what I'm excited to see here is that our business case is very solid, because you see that we have a margin of 120 Swiss francs per square meter that we can use to develop and to make this into a profitable business indeed. So we have been doing a lot of work. Again, I shouldn't be showing you this, but just to give you a little bit of an insight how we are approaching this, the key thing on the bottom right is that we have developed a robust formwork system that has almost no embodied emissions, that can be taken apart, reused for other molds and so on. We are looking at all the details to scale it up so that it can be applied at large scale as well. On the top left, we have been developing new hybrid FE discrete element kind of analysis techniques to be able to generate these geometries and quickly check parametrically to optimize them further. And then on the bottom left, also an example, we have been doing quite a lot of fire tests, material samples, optimizations, and so on to really cover all the things that are needed, because in every single market in Brussels, in Belgium, in Switzerland, we are doing a project in Germany soon. We have to do some sort of a certification process. So there is a lot of work in the background. We built also increasingly large demonstrator, also discretized. Here you see the hinge, how we are solving the hinge, and we're doing all the load tests to benchmark our systems and so on. And I hope you can come and visit us soon, Philippe. Then we have to go to the Hilo project, and next to the Hilo project, we're building a mock-up, a full-scale mock-up for the Swiss project that will feature all of the elements, the prefabricated systems, the integrated kind of piping and so on. And I am so passionately talking about this because, again, 40% of the mass of all these buildings is in the floor plates. I'm fully aware that most of the development will not happen in where I live. Also, still a little bit where you live, but big places of expansion will be Africa, will be India, and so I mean, still China as well, still Europe as well. And that is also where these same ideas actually really make sense. And here I just want to quickly show that we are going even purer for a project in South Africa. We had a commission of the government of South Africa to use their new low strength concrete that uses, instead of aggregates, stone aggregates, it uses shredded wood, so timber waste product. And there we have done some really successful kind of tests. But I want to wrap up quickly because I want to have sufficient time for still a discussion, and sorry for the technical hiccups before. But Tom will talk about it in the third week, so in 2 weeks from now. But I really believe that we all need to collaborate to solve this big challenge of sustainability. remember that I talked about these 3 levers and that it's important to have an attitude or to try to achieve as much as possible of the 3 aspects. How can I activate low carbon materials? How can I reduce the mass of our structure by integrating structural rationale? And how can I, through clever design, detailing, reversibility of details, separation of materials, not gluing things together, how can I think of the end of the lifetime, be it recycling, reuse, and so on? So specifically how I did, or what I showed you, is that we use structural geometry to reduce mass. We use funicular form to have a good geometry to reduce stresses so that we can use lower carbon footprint materials. Digital fabrication, such as direct concrete 3D printing, allows you to reintroduce structural geometry without the waste of single-use molds and so on. I talked a lot, and I hope this resonated with you. This is an example for concrete, but this discrete masonry allows you really to push circular construction and so on. And then this will be more talked about by Tom, but you have to look at the integrated, the full pipeline. You have integrated all of that to talk about really innovation coupled with economics, coupled also with productivity. That means to optimize, speed up kind of the building site and things like that. So with that, I think it's now more than time for me to stop talking and to maybe open up the floor for some questions and hopefully a good discussion. But thanks a lot for your attention.
Great. So thanks a lot, and bravo for the great lecture as usual. So long time no see. So we admire Philippe Brock a lot, especially in China, academic world. We introduced several times, but every time I think Philippe gave even deeper introduction of his research in NCCR. Today you can see a lot of confidential image Philippe show us. We can see a lot of deep more progress BRG and Philippe Brock achieved in over the past few years. So I would like maybe firstly put forward some question. So the floor project, and it's quite interesting because a lot of from the massing geometry to the height of the floor and save a lot of material. And this is a discrete component-based system. So the first question goes to the deformation of the whole the global geometry structure system, including maybe the column and the beams. And in the earthquake, for example, the deformation for the whole system is significant. So how would you like to address the floor system
No, thanks, Philippe. Yes, and actually, I keep forgetting that maybe I should put this already explicitly in my lecture. So how we are approaching, I mean, there's different. Typically, what you would have is that if you have your floors cast in one go, then it's normal that that continuous floor serves as a diaphragm to connect your facades, to kind of transfer the horizontal forces, to activate your lateral bracing scheme, being at a central core or being a facade brace or whatever it is. So in this case, how we are approaching the floor is actually to decouple that, to actually put the floor as a super optimized lightweight infill, an infill in a structural frame. So that means that we need to find diaphragm action in different ways. So a small amount is already taken by the floor, but then what we do is, for example, so in the Brussels, I'll give you 2 examples. In the Brussels project, because it's a tall building, I mean, certainly for Belgium, 130 meters is a tall building. And so it's 27 floors, I believe. And there we basically built in the horizontal plane of the floor, we built a super efficient truss by having super lightweight tension steel crosses in between the frame. And so that gives us a very effective kind of horizontal bracing scheme. In the Zug project, because it's an only 10-story high building, and because the client really wanted to embrace this circularity, and I'll explain what specifically, the engineers are making a fully pre-stressed, prefabricated system. So that means that it's an entirely rigid frame by itself. We just need a little bit of diaphragm action in the floor, but the floor can take it. It's not a problem. And so that's a very different attitude there, because the height is much less high. You can actually just take it in the rigidity of the frame. But so why I believe it's also interesting to not always say, but I need a continuous diaphragm in my structure, is because I've been talking a lot about circularity, demountability. So that also means that what we offer the designers is that you can imagine a next use to the building where you take out different elements. For example, you take out a floor, and that only works if you can decouple those actions. So if your continuous floor is an essential component to the global stability of your building, then of course you cannot upgrade that system. You cannot take it out. You cannot kind of do the full circular kind of thinking. So those are some of the attitudes that we're having. Of course, actually, maybe I should also say that what I showed here works for 85% in the world, but not, for example, for San Francisco, for Tokyo, for Chile, right? So these are not for very heavy seismic regions, but even there it will be interesting in the next years to actually demonstrate that there is quite some value there as well, because locally the floor by itself is stable. Because of its geometry, it can take any loading case, including very heavy seismic loading case, and then we isolate it from the rest of the structure. But what we have is, in seismic, it's very good to have less weight on top. So the lightness of the system actually probably has a very beneficial effect as well. But there, I have to say, step by step, we're now focusing on our market, and then we will see if there is benefits also in seismic areas. But the key thing that I wanted to say is, and maybe I misused your question a little bit, to talk also about in real projects, it's very easy to, at a certain point, to take compromises. Architecture is about compromises, but I find it very important to try to not compromise on the circularity arguments, to not to suddenly start to cast a continuous floor plate because we always do it like that. That is the diaphragm action. So we have to think differently, because if you do that, then you can no longer upgrade, reverse everything, and so on. And so it's difficult in the project, but we fight hard with all our partners and colleagues to keep the purity in there. And I think it will be important.
Great. Another huge discussion recently in China, I also would like to introduce about the 3D printing, concrete printing. Actually, different company achieve different platforms. Construction platforms can reach a very huge scale in the concrete printing, but it's a lot of critical comments put forward to the concrete printing as a structure system, because in your bridge project, it's fantastic to make a compression-only system for the components without tension and steel tension files and other materials. And actually just put them together like the bricks or the rocks, right? So, so I want to know your understanding, and at the same time also we discussed with Archimangus. He actually not a big fan in concrete printing, also makes some criticize on that. So I also would like to have your comments on the future of concrete 3D printing in the industry scale. What do you think on that?
Yeah, so right, I also see some.
Yeah, I have a question.
Yeah, no, actually, thanks for asking that. I think there also we have had some really good kind of experiences, because I mean, You cannot have a more bureaucratic or nervous country than France. In France, you have to show everything, and the regulations are very tough, and the local engineers are very skeptical, and so on. And so we just had the experience, because I told you we are doing a Striatus 2, which we call Phoenix, which is a permanent structure that we're building in Lyon. And there we had a local engineer, and this was very rewarding to us. We gave him the precise geometry, and they did a totally independent, super sophisticated, it must have been super expensive, kind of full abacus analysis of the bridge. And that engineer came back, this bridge is uber safe. This bridge could not be safer. And so the point is that, I mean, what I'm showing is, I mean, yes, it looks new, it's innovative in its fabrication, but it's really based on why these structures are standing for such a long time, right? And so this was good to have that experience, that it was confirmed by an independent engineer, and you could tell that from his conclusion, he was beyond surprised somehow that this was happening. What is a big challenge, though, is actually on the material, and that is something that needs to be accelerated, is that what is the longevity of the material specifically, right? And also because you have these very specific geometries that can catch water, that can have all kinds of freezing and thawing. This material in its form, because there's so many chemicals added to be able to print it, that the long-term behavior of the material is not fully understood. So of course it helps that by having the geometry nice, the stresses are very low, so you can kind of have extremely large safety factors on your stresses and so on. But still, these are some key questions. So now with Holcim, they're doing an accelerated kind of a test to be able to demonstrate this, because the client is asking them to guarantee 50 years design life. So I think a lot is happening there. So I think these questions, it's just a matter of time to get to a maturity of the industry and the solutions provided that we can get there. But then obviously, probably Achim is not that excited about concrete, because the inks, typically, the inks used in the concrete, they usually are more cement-based than concrete. And that means that the ratio of cement, which is the polluting aspect in the concrete, is of course very high. On top of that, in order to be able to print them and to provide sufficient strength early on, these are typically extremely high strength concrete. So you have twice a bad effect. You have a high percentage. So let's say if you reduce the volume of your 3D printed component, well, the entire volume is typically only cement, kind of, and high strength cement. So it's entirely offsetting. So you're not winning anything. It's like casting a full typical kind of concrete section. Okay, that is what everyone thinks. That's what everyone says. But the real world is rapidly evolving. And for example, that is why I made the comment that what we are using in Lyon is 100% recycled concrete, also the cement. So that means like no new embodied emissions except for the crushing, the transport of the materials, the construction, demolition waste, and so on. So why I give you this as a hint is that there is so much energy, so much industry is looking at concrete 3D printing. The inks are being resolved. In the next couple of years, I guarantee you, because I see it in the background, I see that this is happening. We will be printing in concrete, no longer in cements. We will be printing in green concretes, no longer in high strength, high polluting concretes. And so once that is the case, then I think it will be hard to argue that there is no outlook for concrete 3D printing, because concrete 3D printing allows you to reintroduce structural geometry efficiently. You're building structures with sufficient mass so that you have all the beautiful qualities of mass, like thermal mass, acoustical mass, and so on. You have the robustness, you have the fire safety. So all of these things are inherent to the material. But you no longer have single-use materials. You optimize how it's being installed on site, how it comes to site, end to end. So, and actually Shajay Bhushan, my colleague at Zaha Code, who's wrapping up his PhD now, actually, he also argues that a beautiful thing about concrete 3D printing, and then particularly robotic concrete 3D printing, is that you can also imagine a very decentralized kind of industry where local crafts and local a new kind of digital crafts can exist. So it's a decentralized industry where you not always have to go to the big players, but you can actually develop your own design to fabrication kind of pipeline and so on. And that is a big outlook. For example, Shajay is from India. And in India, they are very entrepreneurial, very tech savvy and so on. And the low investments in a robotic arm could offer actually innovation in places where typically innovation would never happen. So I think there's quite a few kind of exciting outlooks for concrete 3D printing. But of course, all of this assumes that we're using concrete, that we're designing also meaningful things with concrete. And we don't just use it as a complex formwork to then cast the structure in with all the reinforcements hidden on the inside and so on, right? So, but I don't know. I think it's nothing is black and white. I think if you understand the 3 levers that I presented, and you apply this to any material, to timber, to concrete, even maybe to carbon fiber, right? Yeah. Then you will be sustainable. So I don't think it's about this material. We need to get past that discussion, I think.
Yeah, great. I think that's the reason why I want to invite you to contribute to Architecture Intelligence as a cover project pavilion, including the project itself, but also including the concept you introduce in the lecture. Because
well, thanks for that, Philippe.
Yeah, huge discussion on the concrete printing. But I think the point you mentioned is super important to the future generation, because we also achieve a lot. So we're looking forward to invite you coming to visit what we're doing in such kind of fabrication process.
I cannot wait. I cannot wait. And I've seen some results of your work. It's extremely impressive. I'm looking forward to coming back. Yes, for sure.
I think you actually, Philippe, played a very important leading roles, and we also influenced a lot by your theory and the methodology working flow you introduced to the world. So thanks a lot for that. We have the final question from the floor, and from Wang Bo. Would you like to ask directly to Ms. Block?
Or I can maybe also I can summarize the question, right? So I think it also relates. It also relates to robustness, to resilience, both in high rises, but also. Of course, we have to really consider. We have to consider alternative load paths and so on, and that is also. I'll give you some small examples in the Hilo project. So the floor that I showed you, 5 by 5 meter with the 3 centimeters, there we had to demonstrate what happens when a quarter of the floor is gone, what happens when the entire shell is gone and only the stiffness remain, and so then it becomes an issue of the deflections become too big, but you can still find alternative paths. That's the thing, right? So we are not optimizing for one loading case. We're optimizing for structural geometry. So we're actually in everything that you see, we're never trying to reduce. We're trying to introduce good structural geometry, and it just happens to then end up with not a lot of volume indeed. So, but we need to demonstrate these alternative load paths. In the Brussels Tower, for example, we keep the tension ties exposed as kind of an architectonic or a tectonism, like Patrick Schumacher would say, a tectonism kind of feature to really show how the system is working. But of course, that is an issue for fire safety. But these ties are only there to control the deformations and the deflections. If there is an extreme fire, then they could just go, and the rest of the frame then takes the forces. But what will happen is that you will have a little bit of deformation. So some hinges will form, right? Some totally safe structural hinges, but we will have more deformation than you feel comfortable with in regular use cases, but no failure. Similarly, in the Zug project, another example that I want to give is that, of course, what happens when one of the columns goes away? So what is the capacity of a floor to settle? And actually the discretizations help. They actually allow the floor to safely settle, so it will not crack uncontrollably. It will settle in a new geometry. And then we have alternative load paths. So the column on top will carry the load if one column is taken out and so on. So again, I was not very explicit about this, but it's good that you ask it. And it was also related to the first question of Philippe, is that, of course, you cannot take any shortcuts on safety. But what I try to kind of argue a little bit in my answers is that we too often just do what we always do. And because we always do it, we think that this is the only way of doing things. And so I think it's important to challenge everything, to not say like, no, but you need, because many people would say you need a continuous screed in your building to guarantee the diaphragm action. Well, I say like, no, wait a second. What is diaphragm action? What do we need to realize? And does it need to happen with a wasteful 5 to 8 centimeter continuous plating concrete? Can we not do it differently, right? And the same with actually guaranteeing secondary load path, like you say, failure catching systems and so on. So yes, we do this, but we always try to see what do we need to achieve rather than let's do it in our typical ways. And so actually, by the way, another strategy would be for the, I'm talking about the floor still, and again, is that what I present now and the number that I present are kind of the holy grail. It's kind of squeezing everything out. The system is super pure, no compromises. Everything is integrated like we want it. That is, of course, not a reality. You can also reintroduce a little bit of material to make simple diagonals in compression in the floor that can give you all the bracing that you need and so on. So the thing is that also, for example, for the prototype, the full-scale mock-up that we're now building in the next month. So we are doing the final prefabrication, all the elements are being made. There, I can without hesitation admit that we're going to put some fibers in the concrete. But we have discussed with recycling experts what is the length of fibers that will not jeopardize an easy recycling. But even though we know that the system is fully unreinforced and can work fully unreinforced, we want this to be accepted. We want to introduce it in the market. So it is clear that the first one cannot be the academically pure one, but we want to do everything to take any risks out. So I didn't talk about this sufficiently maybe, but we have been also increasingly become very pragmatic, Philippe, because we want this to happen and not just to be big statements that everyone is skeptical about. Okay, so there is a question about the application of 3D printed concrete in walls and facade systems and so on. Yes, sure, maybe. I'll give you two by the way, quickly, I take your question as an opportunity, Kimi, to emphasize why we look at floors, because actually columns, walls, gravity typically comes down. We have very efficient bracing systems. So they're actually already quite optimized kind of geometries. The floor, the forces want to naturally go like that. The floor is straight. That is why it's an inefficient system or a problem or a challenge, right? So that's maybe the first point that I want to make, that actually the key challenge is spanning space, not necessarily the other structure. But maybe to the facades, what I was very skeptical when my colleagues proposed it, and they're looking at mono material, fully 3D printed advanced plastics facades that do visual optimization, building systems optimization, whatever, and so on. So, but actually what is rather interesting is that they're using 3D printing of monomaterials so that these can be easily recycled. So that is actually looking at the problem differently. you're not building for extremely long-term durability, but you really customize the performance of the element, but you do it with a material that is 100% and easily recyclable so that you can upgrade finish and so on. So yes, I think there is potential for all of this, but always when you are fully aware of what you're trying to achieve, and if are you really making a contribution? And for me, again, sorry to keep referring back to these 3 levers, but to me, that is a useful framework to check if you're really making a meaningful contribution. Are you aware what you're doing with the materials? Are you aware what you're doing? Are you reducing the mass? Are you using the materials better? And do you have an outlook for the end of life? Recycling, reuse, demountability, and. So I think that's maybe important.
Okay. Any question? I think already time is up because we should.
I saw. Yeah.
So
Sorry,
thanks a lot.
I went a bit too long. But
Thank
I
you so
look
much.
forward to seeing you all next week then again.
Yeah.
Okay.
We're looking forward to see you soon.
Okay,
so,
good.
Yeah, thanks a lot. We're looking forward next week.
Yeah, that's right.
The graphic statics, that is extremely important, interesting part to us. Thank you.
Fantastic. Okay, see you next week. Thanks, Philippe. Thanks, everyone. See you next week.
Bye-bye.